Okay, in this example of two variance testing, hypothesis testing, a restaurant manager is designing a system that is intended to decrease the variance of time customers wait before their meals are served. Under the old system, a random sample of 10 customers had a variance of 400. I noted that that is the larger of these two. Under the new system, a random sample of 21 customers had a variance of 256. At a 10% alpha, is there enough evidence to convince the manager to switch to the new system? Assume both populations are normally distributed. That information should be given to you. Okay, just like always, we're going to have to identify our null and alternative hypotheses. The null is that the variance of the first population is equal to the variance of the second population, or the ratios of these two variances is equal to 1. The alternative is that the first variance is larger than the second variance, and that's where our claim is, or that the ratio of these two is greater than 1. Okay, when I found the confidence interval, or I'm sorry, the critical value here, I looked at the confidence level was 90%, alpha was 10%, so I went to that chart. Degrees of freedom for my larger variance, is 400. It had a sample size of 10, so that degree of freedom would be 9. My smaller variance had a sample size of 21, so its degree of freedom would have been 20. So where those two intersected on this table, alpha 10 table, we found the critical value of 1.94. Okay, doing our test statistic, again, we set the larger variance over the smaller variance. So that was 400 over 256. We come up with a test statistic of 1.56, which is not as great as this critical value that we found on our F distribution. When we draw our table here, draw our distribution, that is not a very good distribution if it's a F distribution, but we can see that our test statistic is closer to 1 than the critical value. Now the p-value, you're going to have to go to StatCrunch, and I definitely want you to be able to do all of these on StatCrunch. You're going to go to Statistics, down to Variance Statistics, to Sample, and this time with Summary. So it's set up for you. You put your data in for each sample. My first variance was 400. The sample size on that was 10. It'll calculate the degree of freedom. My second variance was 256, and its sample size was 21. I'm doing a hypothesis testing, assuming that the ratio is equal to 1. This was a right tail because we're assuming the first one was larger, so we need to specify that. And then I'll click Compute. I come up with my 1.56 F statistic. My p-value is 0.1939. So that is how I got that. Now I'm not going to ask you to do a confidence interval, but I want to show you how that would work because it's not different from anything we've done before. I just know that you're not going to be asked this on my math lab. But you go to the Edit, same thing, we're going to click the confidence interval. But remember, this was a right tail test where we had 10% alpha in the right tail. And the confidence interval that is going to have 10% in that right tail is going to be 0.8. And when we do that confidence interval, we get this lower limit of 0.795 and an upper limit of 3.591. And because 1 is in that interval, that also supports the outcome that we had with our p-value and our critical value. And now this seems kind of weird, and this is why I wanted to show you this, is previously we were looking at if 0 was in the confidence interval, we could not reject the null hypothesis. But now we're looking at 1 is in the interval, and so we are going to fail to reject the null hypothesis because we are looking at a ratio of 1. We're trying to see how close we are to that. So that's why this is different here. But the p-value is high, the null must fly. We can see our test statistic is not in the rejection zone, so we would fail to reject the null hypothesis. There is not enough evidence to support the claim that the new system is better. And I would assume that that new system, 400 is much somewhat higher than the 256, but that small sample size probably gave that less power. Okay, so I'm going to move on and do our last hypothesis test in this section. You want to purchase stock in a company and are deciding between two different stocks. Because a stock's risk can be associated with the standard deviation of its daily closing prices, there's a lot of variance in that closing price. You're going to think twice about that. You randomly select samples of the daily closing prices for each stock to obtain results. At a 5% alpha, sorry that slipped, can you conclude that one of these two stocks is a riskier investment? Assume that stock closing prices are normally distributed. This is a really good business example of how you would use hypothesis testing. Also, I want you to recognize that our problem is giving us standard deviation. So we need to be aware of that. Hypothesis testing with variance with the F distribution is looking at the ratio of variances. So we're going to have to make an adjustment. So we have two stocks, sample size 30, standard deviation of 3.5. Sample size 31, standard deviation of 5.7. Stock B has our larger standard deviation, but in each of these I need to square both of these values because we know we're going to be comparing variances. Okay, going back to our regular lineup when we're dealing with hypothesis testing, we have to write our null and our alternative hypothesis. The null is always that the two variances are equal to each other, or that the ratio, because they're equal to each other, close to equal to each other, is equal to 1. Okay, the alternative in this case is we're just comparing to see that if it's not equal to each other, if one is riskier than the other, we don't know which one. So we're going to say that the variances are not equal to each other. That's where our claim is. If they are not equal to each other, we know that the ratio is not equal to 1. The confidence interval or level was 95. Our alpha was 5%. Our degrees of freedom for our variance, our sample that had the larger variance had a sample size of 31, so its degree of freedom was 30. The degree of freedom of the other was 29, given that that sample size was 30. So I would go to the F distribution for 0.05 alpha. I'd find the column and the row where these two intersect, and I would get the critical value of 2.09. Okay, so that's how I found that. Our test statistic, again, we are given standard deviation, and we have to square each of those. So I wrote that all in here, looking at the standard deviation squared over my second standard deviation squared. I come up with these two this F statistic from these two variances. So we come up with a F statistic of 2.652. When we compare that to the critical value, it is greater than the critical value. When I draw my critical value curve, I can see that my test statistic is in the rejection zone. Again, I'm going to have to go to StatCrunch to do the p-value. I'm going to have to close out my last problem. But again, I'm going to go to Stat, Variance Statistic, to Sample with Summary. Now I need to put in my variance, I need to put in the variances, not the standard deviations. So my variance for the first sample, the larger of the two, is 32.49. And its sample size was 31. Sorry, that keeps hiding on you. Okay, the second variance was 12.25, and that sample size was 30. Okay, I'm doing a hypothesis test. The null is that they're automatically equal to 1, and it's already set to the default that they're not equal to 1. So that's good to go. I can go ahead and click Compute. I come up with my test statistic of 2.652, and I have a p-value of 0.0102. Now keep in mind, because that p-value is low, the null must go. That matches up with what we came up with the critical value, but I want to show you the the confidence interval again. I go to the confidence interval because this is a two-tailed test and we're doing 5%. My 5, that's automatically set up, ready for us to go. When I click the compute, I get the lower limit of 1.2, upper limit of 5.2. This is our variance interval. If you would need to find the standard deviation interval, you would have to square root each of those. But in this case, 1 is not included in the interval. The lower limit is greater than 1. So that matches up. So looking at our 3 different methods, again, I don't think you have to do the confidence interval method in StatCrunch. P-value, though, you will be asked for, and StatCrunch would be the way to find that. The critical value, I don't think you're going to be asked that in my math lab, but you will be on a test. I will give you the critical value. In each of these cases, we could see that all 3 methods support that we will reject the null hypothesis. There is enough evidence to support the claim that stock B must be riskier due to the larger variance. So going back up here, that larger variance says that that's a riskier stock.